Welcome, everyone. When you interact with a highly responsive, globally available web app today, you're really experiencing the culmination of incredibly complex distributed systems and high availability environments. So today, in this explainer, we're going completely under the hood to demystify the magic behind the apps you use every single day. We are moving way past those basic multi-tier setups of the past, and we're exploring the massive, highly concurrent architectural frameworks required to actually operate and scale at a global level. Let's get right into it. Here is our structural blueprint for this explainer. We'll be looking at 1. The web's digital blueprint, 2. Essential architectural components, 3. Monoliths to agile microservices, 4. Shaping the user experience, and finally, 5. Frameworks for every environment.
Okay, let's dive into this with Section 1, the web's digital blueprint, foundations of the web.
So, at its absolute core, web application architecture is the structural framework governing exactly how clients, servers, and databases interact. But look, in a modern production environment, this blueprint goes way beyond simply connecting components together. It dictates how a system achieves true fault tolerance and high availability. It defines whether your application relies on horizontal scaling, dynamically adding more nodes to a cluster, or vertical scaling, by beefing up the compute power of your existing hardware. Having this meticulously designed blueprint is absolutely essential for achieving scalability, security, and reliability. It's what eliminates single points of failure and establishes distributed state management. That way, if one availability zone goes offline, boom, the system dynamically reroutes traffic without the end user ever noticing a single blip in service.
To really understand the stakes here, we have to remember we've evolved far beyond the era of static websites. Those were basically just digital brochures that used simple stateless HTTP requests to fetch flat HTML documents from a single server. Today's interactive web applications, they are dynamic, living engines, and they impose completely different structural demands on our systems. We are dealing with robust API-driven data layers, incredibly complex client-side state management, and the absolute necessity of handling persistent, bidirectional communication protocols like WebSockets. These dynamic engines have to continuously parse enormous JSON payloads, manage concurrent user sessions, and synchronize data in real time across multiple globally distributed databases. It is a whole different ballgame.
Moving right along to Section 2, Essential Architecture Components, the traffic cops.
DNS, or the Domain Name System, is the absolute starting point of the routing process. It's the address book that translates human-readable domains into IP addresses to make sure the user actually finds the house we've built. But in high-performance architecture, DNS is way more than just a simple lookup mechanism. Modern DNS configurations leverage latency-based routing to automatically direct users to the server physically closest to them, which dramatically reduces network lag. They also use geolocation routing to serve region-specific content or to strictly comply with local data sovereignty laws. Plus, engineers have to carefully manage DNS time-to-live settings and propagation times across global Anycast networks to ensure immediate failover during an outage so users aren't left stranded with stale IP addresses. Have you ever tried to buy hot concert tickets online and somehow the site didn't crash? Well, you can thank a load balancer for that. These are the crucial systems that distribute incoming network traffic across multiple backend servers. At an architectural level, you're typically choosing between Layer 4 and Layer 7 load balancing. Layer 4 operates at the transport level, routing traffic purely based on IP addresses and TCP ports, which makes them incredibly fast and resource efficient. But Layer 7 operates higher up at the application layer. This allows for much more intelligent routing based on HTTP headers, cookies, or the specific URL path requested. By using advanced distribution algorithms like round-robin or least connection routing and combining them with continuous automated health checks, load balancers ensure maximum throughput and prevent any single node from becoming a bottleneck. Now, what's really interesting about this slide is how caching acts as a massive shortcut. Caching services are high-speed data storage layers sitting perfectly between your application code and the database. Because let's face it, fetching data repeatedly from a traditional relational database is just computationally expensive and slow. But if you implement in-memory caching clusters using tools like Redis or Memcached, applications can serve frequently requested data in literal microseconds, lightning speed. However, this introduces one of the absolute hardest problems in distributed systems, cache invalidation. Deciding exactly when and how to clear stale data without causing a sudden, massive spike in database queries, known as a cache stampede, requires highly sophisticated write-through or write-behind strategies. And when you push this out to the edge via content delivery networks, caching aggressively eliminates latency for users worldwide. Let's walk through this seamless sequence, highlighting the critical metric of time to first byte, or TTFB. Step 1, the user clicks a link. Step 2, DNS resolves the routing. Step 3, the load balancer securely distributes the request. And Step 4, the cache or application server processes and delivers that fast data. While this entire flow happens in mere milliseconds, optimizing that specific sequence across global edge networks is the defining characteristic of elite engineering teams. They are constantly battling to reduce physical network latency, minimize the overhead of TLS handshakes for secure connections, and optimize database query execution plans to ensure the time between the user's input and the first byte of data hitting their browser is virtually imperceptible.
Which brings us to Section 3. Monoliths to agile microservices, the infrastructure shift.
Now, monolithic setups kind of sound like a terrifying boulder from an Indiana Jones movie, right? And honestly, they can be just as hard to maneuver. Monoliths contain the entire application, the UI, the business logic, the data access layers, all within a single codebase and deployment payload. While they are simple to develop initially, they inevitably suffer from tightly coupled dependencies. A single memory leak in one tiny submodule can literally crash the whole application, and deployment pipelines become massive bottlenecks, where engineering teams are constantly blocking each other. That's why pivoting to agile microservices feels like a massive relief. It's like working with digital Lego bricks. Microservices decouple these domains into independent, loosely coupled services. Isolated teams can write, test, and deploy using entirely different tech stacks and independent CI/CD pipelines. And more importantly, you get independent scaling. If a specific reporting service is under heavy computational load, you dynamically scale just that microservice, rather than duplicating the heavy footprint of the entire monolithic application.
But the evolution doesn't stop at microservices. Serverless options are pushing the boundaries of how efficiently we can scale our systems, providing ultimate agility. They completely abstract away the underlying infrastructure. Developers just deploy discrete functions, and the cloud provider dynamically allocates compute resources on demand per execution. It's amazing, but it does introduce entirely new architectural challenges. Engineers have to precisely account for cold starts, where initial execution latency spikes because the function's container is literally spinning up from scratch. Plus, moving to serverless forces a strict transition toward event-driven architecture. That fundamentally changes how applications are written, debugged, and monitored, often requiring complex asynchronous tracing just to track data payloads across dozens of independent functions. Let's shift our focus from the back-end infrastructure for a moment and look at Section 4, Shaping the User Experience, Front-End Delivery.
And this brilliantly illustrates how users actually interact with the data on their screens. We're primarily evaluating single-page applications against server-side rendering. SPAs shift the rendering burden entirely to the client's browser. They download a thick JavaScript payload up front and then dynamically rewrite the document object model as the user navigates. It creates a highly dynamic, fluid experience. Server-side rendering, conversely, is a much more robust, preloaded approach. It generates the full HTML on the server per request, returning a fully rendered page to the client, which dramatically improves initial load times and search engine optimization. Interestingly, today, modern meta frameworks like Next.js and Nuxt are actually blurring these historical lines. They allow architects to implement hybrid approaches, using static site generation or incremental static regeneration alongside client-side hydration to get the best performance profiles of both methodologies simultaneously.
Ultimately, whether you choose an SPA or SSR, the ultimate goal of the blueprint is captured perfectly in this quote: designing efficient systems that meet both technical requirements and user expectations. It is a rigorous exercise in balancing architectural trade-offs. You have this constant, unavoidable tension between delivering heavy, feature-rich JavaScript applications and the strict user demand for sub-second paint times, especially on high-latency mobile networks. Every single architectural decision is a calculation of bandwidth limitations versus processing power on client devices. You are constantly balancing strict core web vitals like largest contentful paint and cumulative layout shift against the sheer complexity of the underlying back-end data aggregation.
Let's look at how we adapt these tools in Section 5, Frameworks for Every Environment, Tailoring the Build.
Because web architecture isn't one-size-fits-all, right? Different digital spaces require highly specialized tools, and the underlying environment fundamentally dictates your architectural toolset. Let's rapid-fire through these. First, in large-scale enterprise environments, heavy-duty Java frameworks like Spring Boot provide the strict typing, JVM tuning capabilities, and robust dependency injection required for maintaining massive legacy integrated transactional systems. Next, in cloud ecosystems, architecture shifts entirely toward containerization. Orchestration platforms like Kubernetes manage thousands of Docker containers, natively handling automated rollouts, self-healing, and service meshes for complex inter-service communication to scale seamlessly. Meanwhile, mobile environments shrink down and present a completely different paradigm altogether. Mobile architecture has to optimize for highly constrained memory, aggressive battery management, and intermittent network states, using offline-first strategies, local SQLite databases, and complex background state synchronization. So we have moved from simple stateless web architectures to globally distributed microservices and highly optimized edge-computed applications. But the landscape continues to shift rapidly. As user expectations continually demand instant gratification, what will the web's blueprint look like tomorrow? With emerging paradigms like WebAssembly running directly on edge nodes and CDNs, we are pushing the very definition of architecture completely out of the traditional data center and right into the client's hands. It is a deeply fascinating engineering space to follow. Thank you so much for joining this explainer, and keep exploring the incredible architecture that powers your digital world every single day.